The universe holds a secret pattern where we thought only randomness existed. This is the mystery of unexpected symmetry in deep field star systems, a discovery that could rewrite our cosmic story. By the end of this video, you will understand a finding that challenges the very laws we thought governed everything. Why would ancient galaxies arrange themselves with such intricate order? What hidden force could have written this blueprint into the fabric of reality? How does it feel to know the cosmos might be more structured than we ever dreamed? That single patch of darkness, chosen almost at random, became a window into infinity. Astronomers aimed the Hubble Space Telescope at what they believed was an empty void, a blank space between the stars, and they kept its eye open for 10 entire days. The light, ancient and faint, slowly gathered on its sensors. When the final image was processed, it revealed not emptiness, but a spectacular crowd. Thousands of galaxies, each a swirling island of billions of stars, filled a speck of sky no larger than a grain of sand held at arm's length. This was the Hubble Deep Field, a moment that instantly multiplied our known universe. We went from a quiet neighborhood to a sprawling, vibrant metropolis. The sheer density was staggering, forcing a complete rewrite of how quickly and how many galaxies formed after the dawn of time. But amid this glorious cosmic census, something else, something quieter, began to nag at the scientists. The prevailing wisdom, the cosmological principle, stated that on the largest scales, the universe should be smooth and uniform like a well-mixed batter. Matter should be spread evenly in all directions, leading to a random, isotropic scattering of these distant island universes. Yet, as they stared at this mosaic of light, some researchers felt a flicker of doubt. The galaxies did not look entirely random. There were faint suggestions of patterns, subtle groupings, and vast, ghostly arcs that seemed to whisper of a hidden architecture. This was the first clue that the cosmos was not just vast, but perhaps intricately organized. The search for its blueprints had just begun. Symmetry in the cosmos is far more than a simple mirror image. It is a profound principle of order, a hidden language written into the fabric of space itself. On the grandest scales, cosmologists describe this as homogeneity and isotropy. Homogeneity means the universe looks roughly the same at every location, like a vast, evenly mixed cake. Isotropy means it looks the same in every direction you peer. No matter where you stand, the large-scale properties of the cosmos appear uniform. This idea, a cornerstone of modern cosmology, suggests that if you zoom out far enough, the distribution of matter should settle into a kind of statistical sameness. The universe should not have a favorite spot or a special direction. Yet the symmetry whispered by the deep field images is something different, something more intricate. It is not the broad, predictable uniformity of a smooth batter, but a delicate, fine-grained pattern woven into the apparent chaos. Think of it like the difference between a quiet, consistent hum and a complex piece of music. Both have a pattern, but one holds layers of unexpected harmony. Experts describe this not as a perfect geometric shape, but as a statistical symmetry. It reveals subtle correlations in where galaxies choose to form and how they relate to one another. A faint echo of coordination across unimaginable voids. This nuanced definition is why the discovery is so startling. It challenges us to look deeper, to find the tools that can tease out this subtle cosmic order from the overwhelming noise of randomness. To see this hidden order, we needed to map the cosmos on a scale once thought impossible. This monumental task fell to a new generation of cosmic cartographers, vast automated sky surveys like the Sloan Digital Sky Survey. These projects did not simply take pretty pictures. They methodically cataloged the positions and redshifts of millions of galaxies, one by one. Redshift, a measure of how much the light from a galaxy has been stretched as the universe expands, acts as a cosmic clock. It tells us not just where a galaxy is, but how far back in time we are seeing it. This transforms a simple star chart into a three-dimensional map of the universe, where the z-axis is time itself. With the James Webb Space Telescope now joining this effort, peering even deeper into the infrared, these maps have become astonishingly detailed, covering vast and separate patches of the sky. It is this immense, statistical firepower that changed everything. Finding a subtle pattern in a handful of galaxies is like trying to hear a whisper in a storm. But with a sample of millions, that faint whisper becomes a clear, repeating chord. The pattern of symmetry was not visible to the eye in any single image. It was a ghost in the data, a statistical signature that only emerged when astronomers could compare the distributions from these deep fields. They were looking for correlations, for structures that seemed to relate to one another across billions of light years. The data from these surveys provided the empirical backbone, the solid ground on which the extraordinary claim of cosmic symmetry could stand. But how do you actually find a ghost? The answer lies in the sophisticated analytical methods that learn to read the universe's hidden language. These statistical tools are the keys that unlock the hidden language of the cosmos. To understand their power, picture a vast, dark ocean at night. With your naked eye, you might see a few scattered points of light from distant ships. You could guess they are random, but you cannot be sure. Now, imagine you have a special lens that reveals not just the ships, but the subtle, underlying currents that connect them. This is what the two-point correlation function does for the universe. It measures the probability of finding two galaxies at a specific distance from one another, comparing it against what a purely random, scattered distribution would look like. When this probability is higher than chance, it reveals the invisible scaffolding of the cosmos, the vast filaments and walls where galaxies prefer to gather, like glitter tracing the lines on an unseen map. Another crucial tool is power spectrum analysis. Think of the universe's structure as a complex musical chord. This method acts as a cosmic ear, decomposing that chord into its individual notes, its constituent waves. It shows us how much structure exists on each scale, from the small, tight groupings of local galaxies to the deep, resonant bass notes of the largest superclusters, stretching across billions of light years. These are not just abstract calculations. They transform the raw, beautiful chaos of a star field into quantitative metrics, hard numbers that can be rigorously tested against the predictions of our most advanced cosmological simulations. And it is here, in the cold, precise language of data, that the mystery truly deepens. The unexpected symmetry astronomers are finding manifests as specific, subtle features in these statistical measures. Certain correlations are stronger than they should be. Specific waves in the power spectrum ring with a peculiar intensity. These are the faint fingerprints of a process we do not yet understand, a signature etched into the infant universe that has persisted for over 13 billion years. What primordial event, what force from the first fleeting moments of time, could have written this pattern so perfectly and so permanently into the very foundations of everything? For generations, the cosmological principle has been the bedrock of our cosmic understanding. It is a simple, elegant assumption that the universe, on its largest scales, has no favorite place and no special direction. This idea of a smooth, uniform cosmos is woven into the very fabric of our most successful models, from the Big Bang to our current standard model of cosmology. It is the reason we can confidently extrapolate the laws of physics from our tiny corner of the galaxy to the farthest reaches of space and time. Yet the discovery of this intricate symmetry in the deep field galaxy distributions sends a quiet tremor through that foundation. If these patterns are real and universal, they could signal a fundamental anisotropy, a cosmic grain, a preferred direction woven into the very structure of reality. Some scientists suggest we might be seeing a local illusion, a statistical fluke within our limited view. a grand cosmic coincidence, but others see the fingerprints of something far more profound. Could the universe have a non-trivial topology, a shape so complex that it folds back on itself in ways we cannot yet see? Might these patterns be an echo from a pre-Big Bang era, a relic from a time before time as we know it began? This is not merely a technical debate over data points. It is a philosophical earthquake, forcing a re-examination of one of astronomy's most cherished assumptions. The cosmological principle is so fundamental that to question it is to question the stage upon which the entire cosmic drama is set. If it holds, we must find a way to explain this delicate symmetry within our existing framework, a puzzle that will push our models to their limits. But if it falters, we stand at the precipice of a scientific revolution, one that would compel us to rewrite the story of the universe's very first moments and consider initial conditions we have never before dared to imagine. This profound symmetry we detect today might be a message from the very first moment of time. To understand how such a delicate pattern could span billions of light years, we must journey back to the universe's first fleeting instance, a period of unimaginable transformation known as cosmic inflation. In less than a blink of an eye, the entire cosmos underwent a violent, exponential expansion, stretching from a subatomic speck to a volume far beyond what we can observe. During this incredible growth spurt, the empty vacuum of space itself was not perfectly still. It was fizzing with quantum fluctuations, tiny, temporary ripples of energy popping in and out of existence. Inflation seized these random, microscopic ripples and stretched them to astronomical proportions, freezing them into the fabric of spacetime as minute differences in density. These imperfections became the cosmic seeds, the slight gravitational overdensities that would, over billions of years, pull in matter to form the very first galaxies, stars, and eventually us. The distribution of galaxies we map today is a direct, blown-up reflection of those initial quantum jitters. This is why the unexpected symmetry in the deep fields is so revolutionary. It suggests that these primordial fluctuations were not entirely random. Certain models of inflation predict that the underlying quantum fields could have produced specific, correlated patterns in these density variations, a kind of resonant harmony written into the cosmos at its birth. If the symmetry we observe matches one of these predicted patterns, it would be like finding a fossilized blueprint from the universe's first fraction of a second. This fossil would not be made of stone but of light, preserved in the afterglow of creation itself. This ancient light is the cosmic microwave background, a snapshot of the universe when it was only 380,000 years old, and it holds the final piece of this cosmic puzzle. That ancient afterglow is our most direct window into the universe's fiery infancy. The cosmic microwave background, a faint whisper of heat left over from the Big Bang, is a snapshot of the cosmos when it was a mere 380,000 years old. Its faint temperature variations, seen as a modeled pattern in data from missions like Planck, are not random noise. They are a precise map of the primordial density variations, the very seeds of all future structure. These are the quantum fluctuations from inflation, frozen in light. For decades, the standard model of cosmology treated this map as the ultimate example of statistical symmetry, expecting its patterns to be evenly distributed across the sky. Yet, upon closer inspection, strange features emerged. Astronomers found a puzzling hemispherical power asymmetry, where one half of the sky shows stronger temperature fluctuations than the other. They discovered a mysterious cold spot, a vast, unusually cool region that is incredibly difficult to explain by chance alone. These are not just minor quirks. They are large-scale anomalies that directly challenge the assumption of a perfectly uniform and isotropic universe. This is where the mystery deepens profoundly. If the unexpected symmetry we see in the deep field galaxies is real and primordial, It must have left its fingerprint on this ancient light. The patterns in the infant universe, imprinted on the cosmic microwave background, should logically connect to the patterns we see in its adult structures, the ancient galaxies. This creates a breathtaking opportunity for a cross-check across nearly 14 billion years of cosmic history. Experts suggest that finding a consistent directional alignment or a shared patterned resonance between a CMB anomaly and the deep field symmetry would be monumental. It would be like finding two pieces of a shattered artifact, one from the beginning of time and one from much later, that fit together perfectly. Such a discovery would point unequivocally to a single, coherent physical process operating at the universe's birth, a process our current models do not account for. Yet this powerful diagnostic tool is complicated by the universe's greatest unknowns, dark matter and dark energy. These invisible components govern the growth of cosmic structure, acting as the scaffolding and the engine for the universe's expansion. Any attempt to connect the infant cosmos to the adult one must account for their profound influence. They are the invisible hands that have sculpted the universe from its primordial blueprint into the grand design we observe today. Untangling their role is the next great challenge in deciphering this cosmic code. This invisible framework of dark matter is the silent architect of our universe. It is the hidden skeleton upon which the luminous galaxies are draped, its gravitational pull guiding the flow of ordinary matter for billions of years. Without this unseen hand, the universe would lack the grand design we observe, the vast cosmic web of galaxy clusters connected by intricate filaments and separated by immense empty voids. Our most powerful computer simulations, which model the evolution of the cosmos with a component called cold dark matter, do an astonishing job of recreating this web-like structure. They show how tiny initial ripples can grow under gravity's relentless pull into the complex universe we see today. Yet these very same simulations, for all their success, present a puzzle. They tend to predict a cosmos that is slightly more chaotic, more randomly scattered than the subtle, ordered symmetry hinted at in the deepest field observations. The simulations give us a universe that looks convincingly real, but the real universe might be even more structured. So what does this discrepancy mean? The unexpected symmetry could be a clue pointing to a deeper nature of dark matter itself. Perhaps dark matter is not entirely cold and non-interacting as many models assume. Maybe it possesses some form of weak self-interaction, a gentle pressure that smooths and organizes its distribution on the largest scales, encouraging the formation of these delicate patterns. Or the answer may lie even further back in time. The symmetry we see today could be a fossil, a direct imprint of an initial condition that was fundamentally more ordered than pure randomness. The dark matter distribution at the very beginning might have already contained a hidden blueprint, a resonant pattern that inflation simply amplified, and which gravity faithfully preserved for over 13 billion years. This mystery is not a small one. To understand the cosmos is to understand dark matter, for its gravitational influence is the dominant force sculpting everything we see. Yet we still do not know what it is. Its nature is inextricably linked to the even more perplexing dark energy, the force driving the universe's accelerated expansion. Together, these two invisible components hold the key to the universe's past and its ultimate fate. The search for this hidden symmetry, therefore, becomes a new way to probe the properties of the cosmos's greatest unknowns, using the large-scale structure of the universe itself as our laboratory. Dark energy is the silent, opposing force to gravity's grand design. While gravity tirelessly works to pull matter together, building the cosmic web over billions of years, dark energy is the counterweight, relentlessly stretching the fabric of space itself and pushing the universe apart at an ever-increasing rate. This accelerating expansion does not just create more distance between galaxies, it fundamentally alters the rules of cosmic construction. In the recent universe, dark energy acts as a cosmic brake on the formation of the largest structures. It makes it more difficult for gravity to pull new matter into vast clusters and filaments, effectively suppressing the growth of the cosmic web on its grandest scales. This is why the subtle symmetry we observe in the deep fields is so puzzling. The patterns in galaxy distributions are fossils from a much earlier era, a time when the universe was smaller, denser, and dominated by matter, long before dark energy's influence became significant. The symmetry was likely woven into the cosmos at its birth, not crafted in its old age. So how could dark energy possibly be involved? The answer may lie not in dark energy alone, but in its potential relationship with its mysterious counterpart, dark matter. Some speculative theories propose a subtle coupling between these two invisible components. Imagine dark energy and dark matter not as separate, indifferent forces, but as partners in a slow, cosmic dance. If they interact even weakly, that interaction could introduce a new, large-scale correlation into the universe's expansion. It could create a faint directional preference, a subtle grain in the stretching of spacetime that might nudge the distribution of galaxies into the symmetrical patterns we are now detecting. Another radical possibility is that our understanding of gravity itself is incomplete on the largest scales. Modified theories of gravity could naturally predict such large-scale correlations, effectively building a hidden symmetry into the force that binds the cosmos. The challenge, and the reason this remains in the realm of theory, is the constancy of dark energy's influence. Any imprint it leaves would be incredibly subtle, a whisper nearly drowned out by the roar of primordial signals and the complex effects of dark matter. Disentangling this faint signature requires measurements of breathtaking precision, pushing our most powerful telescopes and data analysis techniques to their absolute limits. The quest to explain this cosmic symmetry is therefore more than a search for answers. It is a driving force that compels us to build better instruments and develop sharper analytical tools, all to read the faintest handwriting in the grandest of cosmic libraries. The James Webb Space Telescope is now peering into the cosmic dawn, a realm Hubble could only hint at. Its infrared eyes are sensitive to the stretched, ancient light from the very first galaxies, allowing it to witness the universe's nursery in stunning, unprecedented detail. We are not just seeing more galaxies, we are seeing them born. Webb's deep field images provide more than a simple census. They offer a rich tapestry of data on the shapes of these infant galaxies, the types of stars bursting into life within them, and crucially, their precise positions in the primordial dark. With this new clarity, astronomers are spotting something remarkable. The earliest galaxies are not scattered evenly. They appear to be gathering in what seem to be unexpected overdensities, nascent clusters and filaments that suggest a blueprint was in place from the very beginning. Could these be the embryonic forms of the large-scale symmetry we detect in the more modern universe? This is the critical test. By comparing the statistical patterns in Webb's deepest views with those from Hubble's surveys of a slightly older cosmos, scientists can perform a cosmic paternity test. Does the subtle signature of symmetry exist in the infant universe, or does it only emerge later as structure evolves? If the pattern is present in both epochs, it points to a fundamental feature imprinted at birth. If it changes or appears only in certain directions, it suggests a more complex, localized story. Webb is our ultimate time machine for this investigation, its data guiding the next generation of telescopes on where to look and what questions to ask next. But to truly confirm a pattern of this scale, we cannot rely on a single window into the cosmos, no matter how clear. We need to map the entire sky, and that ambition is driving the next great leap in our cosmic cartography. The next generation of cosmic cartography is already taking shape, with observatories designed to read the universe on a scale we can scarcely comprehend. The Vera C. Rubin Observatory, a ground-based telescope with a camera the size of a small car, will begin a 10-year survey of the entire southern sky, not just once, but over and over. It will not simply find billions of galaxies, it will watch them, measuring how their light changes over time to create the most dynamic, three-dimensional map of the cosmos ever assembled. In space, the Nancy Grace Roman telescope will join this effort with a field of view 100 times larger than Hubble's. Together, these instruments will produce a flood of data so immense that the subtle statistical whispers of cosmic symmetry will either ring out with undeniable clarity or fade into the background noise forever. The goal is to shrink the statistical uncertainties that currently leave room for doubt, transforming a tantalizing hint into a concrete, measurable feature of our universe. This is not about taking prettier pictures, it is about gathering overwhelming evidence, one galaxy at a time. But to trace this pattern back to its origin, we must also look deeper into the past, into the ancient light of the cosmic microwave background. Proposed projects like CMBS-4, a network of ultra-sensitive telescopes at the South Pole and in Chile, aim to measure the faint temperature variations of this afterglow with a precision we have never before achieved. They will scour that infant universe map for any subtle anomaly, any directional preference or strange correlation that resonates with the symmetry seen in the galaxy maps. Finding a shared pattern across these two different epochs, the universe's fiery birth and its structured adulthood, would be the smoking gun, the definitive proof that this symmetry is a fundamental relic from the first moment of time. To weave this story together, international teams are planning grand, multi-wavelength surveys. They will combine the optical eyes of Rubin and Roman with the infrared vision of James Webb and the deep, penetrating gaze of new radio telescopes. This unified approach builds a composite, all-seeing view of cosmic structure, allowing us to see not just where the galaxies are, but how dark matter guides them and how dark energy pushes them apart. The sheer volume of information from these future projects will be staggering, a deluge that will either solidify our most revolutionary ideas or wash them away as intricate illusions. This is the dynamic, unpredictable heart of scientific discovery, where every new answer demands a better question, and every map of the cosmos reveals just how much we have left to explore. Theoretical physicists are now racing to build the frameworks that could explain this cosmic blueprint. Their models stretch the boundaries of our imagination, suggesting a universe far richer and more intricate than we have ever conceived. One compelling avenue re-examines the inflationary epoch itself. Perhaps the quantum field that drove the universe's explosive birth was not a single, simple entity, but a more complex structure. Certain models propose that this field could have contained resonant frequencies, like a plucked string, imprinting a specific, correlated pattern onto the density of the infant cosmos. This would naturally produce the large-scale symmetry we observe today, a fossilized echo of that first cosmic vibration. Other theories look to even more exotic relics from the early universe, such as cosmic strings. These are not strings in the everyday sense, but hypothetical, incredibly dense flaws in spacetime, one-dimensional cracks that formed during a phase transition as the universe cooled. As they stretched and vibrated across the expanding cosmos, their immense gravitational pull could have shepherded matter into vast, symmetrical sheets and filaments, weaving order into the primordial chaos. Then there is the staggering possibility of the multiverse. In this view, our entire observable universe is just one bubble in an infinite, frothing sea of universes, each with its own unique physical constants. The unexpected symmetry we see might not be a universal law, but a local artifact, a unique feature of our particular cosmic bubble. It would be the fundamental characteristic of our home, much like the specific arrangement of continents makes Earth distinct from any other planet. Beyond these ideas, some physicists are questioning the very nature of gravity. Our most successful theory, Einstein's general relativity, has passed every test with flying colors. Yet, could it require modification on the very largest scales? Alternative theories of gravity can naturally predict specific large-scale correlations in the distribution of galaxies, effectively building a hidden symmetry directly into the force that sculpts the cosmos. The beauty of this theoretical frenzy is that these are not just abstract ideas. Each model leaves a distinct fingerprint. One might predict the symmetry should be strongest in a specific direction, while another forecasts a unique signature in the polarization of the cosmic microwave background. As new data pours in from telescopes like James Webb and the Vera Rubin Observatory, we are not just collecting more facts, we are conducting a grand cosmic trial. Each theoretical model is a defendant, and the data is the jury, poised to convict the wrong ideas and elevate those that match reality. This process pushes the very frontiers of fundamental physics, forcing us to confront profound philosophical questions. Are the laws of physics truly universal, or could they be a local byproduct of our cosmic address? Is the universe we see the only possible one, or merely one page in an infinite library of realities? The search for the origin of this symmetry is more than a technical puzzle. It is a journey to understand our place in a cosmos that may be fundamentally and beautifully patterned. This discovery of a hidden cosmic order reaches far beyond equations and data, touching the very core of why we look to the stars in the first place. For centuries, a guiding assumption in cosmology has been the anthropic principle, the idea that the universe must be compatible with conscious life because we are here to observe it. This often implies a certain amount of cosmic luck, a random lottery of physical constants that just happen to allow for galaxies, planets, and us. But what if the universe is not a product of sheer chance? The subtle symmetry woven through the galaxy distributions suggests a cosmos where the fundamental laws may inherently favor certain beautiful, coherent patterns. This is not a universe that stumbled into order, but one that was born with it. This idea resonates with a very old human intuition, a thread connecting the mystical harmonies of Pythagoras, who saw the universe as a manifestation of mathematical ratios, to Johannes Kepler's lifelong quest to find the geometric music of the spheres. They believed the cosmos was fundamentally rational and beautiful, and modern science may now be revealing they were right in a way they could never have imagined. The profound question then becomes, is this symmetry a necessary, inevitable outcome of the laws of physics, an emergent property of a mathematical reality? Or does it point to something even more startling, a universe with a specific, perhaps even fine-tuned initial state, set with exquisite precision at the moment of its birth? This moves the discussion from how the universe works to why it is the way it is at all. For us, gazing up from our small world, finding this hidden symmetry feels like receiving a message. It is a cosmic reminder that our search for knowledge, our science and our mathematics, can reveal profound truths about a reality that operates on scales far beyond human experience. It connects the technical analysis of millions of data, points to our eternal search for meaning, suggesting that the cosmos is not just vast, but also deeply intelligible. This philosophical dimension adds a layer of awe to the scientific pursuit, transforming the cold map of galaxies into a testament to a universe that we can, against all odds, understand. And the way we share this understanding, the story we tell about our place in this grand design, becomes the final, crucial piece of this cosmic puzzle. Sharing this cosmic mystery with the world is an adventure in translation, turning intricate data into a story everyone can feel. The challenge lies in conveying the profound meaning behind subtle statistical correlations and theoretical physics without losing the sense of awe. How do you help someone see a pattern that is not visible to the naked eye? A harmony written in the language of mathematics. Science communicators and visualization experts become the essential bridge, crafting immersive videos and interactive simulations. These tools transform the abstract into the tangible, allowing anyone to fly through the cosmic web, to zoom from a single galaxy out to the vast supercluster filaments, and to witness for themselves the potential echoes of order. In planetariums, this experience becomes a shared journey. Under a dome that becomes a window to the universe, light projections trace the grand architecture of galaxies, making the invisible scaffolding of dark matter and the hints of symmetry a visceral, breathtaking spectacle. These are not just lectures, they are invitations to explore, designed to spark that fundamental question in a young mind, a question that might one day lead to a new discovery. This story of unexpected symmetry is a powerful catalyst for inspiration. In an age of immense datasets and powerful algorithms, it proves that the cosmos still holds profound, fundamental surprises. It demonstrates that science is not a static list of facts, but a living, breathing process of collective wonder. This progress relies on a global conversation, on telescopes scattered across continents and in space, and on the diverse perspectives of scientists from every culture working together to decode the universe. By communicating this journey effectively, we do more than share knowledge. We welcome everyone into the ongoing, collaborative quest to understand our place in the grand design. This global collaboration is the engine of modern discovery. The European Space Agency's Euclid mission, for instance, is not a solitary European project, but a vast international partnership. Its goal is to map the dark universe, charting the invisible influence of dark matter and dark energy by observing billions of galaxies. This monumental task requires the combined brainpower of scientists from dozens of countries, each contributing unique skills in instrumentation, data analysis, and theoretical modeling. Similarly, the breathtaking deep field images from the James Webb and Hubble telescopes are the products of international teams who design the observations, process the raw data, and spend countless hours interpreting the results. No single nation, no single university could shoulder this burden alone. The investigation into cosmic symmetry demands this scale of cooperation. It begins with the raw data, a torrent of information so immense that only distributed computing networks across multiple continents can handle the initial processing. This data is then analyzed by large consortia, where astronomers pinpoint galaxies, physicists model gravitational lensing, statisticians search for subtle correlations, and computer scientists write complex algorithms to simulate the cosmos. This interdisciplinary environment is a crucible for innovation. When a statistician from one country questions an astronomer's assumption from another, or when a computer model from one team challenges the findings of another, it forces everyone to think more deeply and defend their conclusions rigorously. This constant cross-pollination of ideas is what prevents groupthink and ensures that extraordinary claims, like the discovery of a fundamental cosmic symmetry, are subjected to the most intense scrutiny. The process is upheld by a foundational principle of science: open data. The deep field observations from these great telescopes are not kept secret. After a proprietary period, they are released to public archives, accessible to any researcher in the world. An independent scientist, perhaps with a completely fresh perspective, can download the same data and try to reproduce the results. They might find a different statistical approach that explains the symmetry without invoking new physics, or they might find even stronger evidence that the pattern is real. This global, transparent system of verification and peer review is what builds confidence in our final answer. It transforms a tantalizing hint from one team into a robust, evidence-based feature of our universe, or it reveals it as a beautiful statistical illusion. This collective endeavor shows humanity at its best, setting aside borders to unite in a shared quest to understand our cosmic home, a testament to the power of curiosity to bring us all together. For every extraordinary claim, a chorus of critical voices rises to ask the essential questions. Could this subtle symmetry be a magnificent illusion, a trick of our own making? The scientific process demands that we listen carefully. One of the most scrutinized possibilities is systematic error. Our telescopes are not perfect eyes, and the complex software pipelines that clean the raw data, removing cosmic rays and calibrating the faint light, could inadvertently introduce subtle, correlated patterns. Imagine trying to listen to a faint, distant melody, but your headphones have a slight, persistent hum that mimics one of the notes. Astronomers must work tirelessly to prove the hum is not coming from their own instruments. Another profound challenge is the selection effect. The Hubble and James Webb Deep Fields are not random snapshots. They are carefully chosen windows, clear patches of sky largely free from nearby bright stars and galactic dust. If we are unconsciously selecting regions that already sit within a particular large-scale environment, we might be studying the cosmic equivalent of a single, well-planned neighborhood and mistaking its layout for the blueprint of the entire city. Some researchers point to known giants like the Sloan Great Wall, a colossal filament of galaxies so vast it challenges the definition of a structure. From our particular vantage point, could such a behemoth be projected onto the deep field, creating a false impression of a universal pattern? This rigorous, often uncomfortable process of self-interrogation is the true engine of discovery. It forces innovators to build stronger cases, to test their findings across multiple, independent datasets, and to refine their statistical methods until only the most resilient signals remain. By confronting these skeptical viewpoints head-on, the scientific community builds an unshakable foundation for any eventual breakthrough. This is how we separate a fleeting mirage from a true feature of reality, preparing us to ask what this structure, if it is real, might ultimately become. This hidden symmetry now faces its ultimate test, a future shaped by relentless expansion. Dark energy, the mysterious force accelerating the cosmos, does not just create more space between galaxies, it fundamentally alters the rules of cosmic construction. In the distant eons to come, the formation of new structures will cease entirely. The universe's great construction sites will fall silent. As space stretches at an ever-increasing rate, the gravitational pull between distant galaxies will grow too weak to overcome the cosmic push. The grand cosmic web, with its delicate filaments and vast walls, will begin to thin and pull apart. Existing galaxy clusters will become isolated islands, drifting forever away from one another into an ever-cooling, ever-darkening void. Within this grand narrative of dissolution, the fate of our mysterious symmetry hangs in the balance. If it is a real feature woven into the fabric of the cosmos, what becomes of it? Cosmological simulations that project trillions of years into the future offer a sobering vision. One possibility is that the pattern will simply become more and more diluted, its subtle correlations stretched across such immense distances that they fade into insignificance, like a signature written in ink that slowly bleeds across an infinite page. Alternatively, the symmetry might fossilize. As the universe expands and structure growth freezes, this primordial pattern could become locked in, a permanent relic of a more dynamic, interconnected age. It would be a ghostly imprint, a cosmic fossil that future observers, if any exist, could still decipher from the positions of the remaining isolated galaxy clusters. The most extreme possibility is that the symmetry could be entirely erased. The relentless stretching of spacetime might randomize the positions of galaxies so completely that all traces of the original blueprint are washed away, leaving behind a cosmos that is not just dark, but fundamentally shapeless. This long-term view connects a specific, puzzling finding to the ultimate destiny of everything we see. It transforms the search for symmetry from a technical investigation into a profound meditation on transience. The grandest architectures of the cosmos, from the smallest galactic clusters to the largest imagined patterns, are not permanent. They are temporary features in an evolving reality, brilliant but fleeting expressions in a much longer story. This perspective does not diminish the discovery, it elevates it. By understanding how this symmetry evolves or how it fades, we gain a unique window into the final chapters of cosmic history. A reminder that to study the universe is to witness a story of both beautiful creation and eventual release. This search for cosmic order is now forging entirely new tools for seeing. The subtle symmetries hidden within billions of data points are pushing the limits of our analytical power, demanding a revolution in how we process information. Traditional statistical methods, while powerful, can sometimes miss the forest for the trees, struggling to identify the most complex, non-obvious patterns woven into the cosmos. This is where a new generation of artificial intelligence enters the story. Scientists are now training deep learning networks on vast, realistic cosmological simulations, teaching these algorithms what the universe looks like under different theoretical models. Once trained, these networks can scan real observational data, acting as cosmic pattern recognition engines. They do not replace traditional tools like the correlation function, but they complement them, offering a fresh, powerful lens that can spot unusual features or hints of symmetry that might otherwise slip through the cracks. This has given rise to a specialized field known as astrostatistics, entirely dedicated to creating analytical methods for the unique challenges of astronomy. Astronomical data is messy, filled with measurement errors from our imperfect instruments, gaps where data is missing, and the strange, complex geometry of our light cone, the finite slice of the universe we can actually observe. Untangling a true cosmic signal from this noisy background requires brilliant new statistical techniques. The impact of this technological push extends far beyond the halls of astronomy. The machine learning algorithms refined to find faint symmetries in galaxy distributions are now being adapted to spot subtle patterns in other incredibly complex datasets. In medical imaging, similar neural networks can analyze scans to identify the earliest signs of disease, patterns invisible to the human eye. In global finance, these tools can model complex market risks, searching for fragile correlations in economic systems. This is the beautiful, often unexpected, payoff of fundamental research. The quest to understand the largest structures in existence is yielding tools that help us understand the human body and our own societies. With each algorithmic advance, we sharpen our vision, transforming an overwhelming flood of raw data into a clear stream of insight about the profound order of the cosmos. This cosmic mystery is more than a scientific breakthrough. It is a living classroom for minds of all ages. For a university student studying cosmology, the unfolding story of unexpected symmetry is a perfect case study in the scientific method. They can trace the entire process from the initial, baffling observation in the Hubble Deep Field, through the formulation of competing hypotheses, and into the complex world of theoretical modeling with inflation and dark matter. It teaches the rigorous statistical tools used to analyze galaxy distributions, moving beyond abstract equations to show how we actually test our grandest ideas about the universe. This topic makes the interplay between theory and observation tangible, demonstrating that modern astrophysics is a dynamic conversation, not a set of settled facts. For younger students, the journey begins with wonder. A simplified, vibrant deep field image filled with thousands of tiny, glowing galaxies becomes a cosmic "Where is Waldo?" Challenging them to find patterns, to trace imaginary lines connecting the dots of light, introduces the fundamental scientific act of looking for order in nature. This simple activity plants a seed, showing that science is not about memorizing answers, but about the thrill of the search itself. The educational power deepens with hands-on experience. Many public galaxy catalogs from missions like Hubble are available online. allowing students to work with the same raw data as professional astronomers. A classroom project might involve classifying galaxy shapes, or even using basic software to search for correlations in their positions. This transforms students from passive learners into active participants in the process of discovery. They experience the same excitement and frustration that researchers feel. The moment you might see a hint of a pattern in your own analysis, a small personal connection to a vast cosmic question. This approach does more than teach facts. It fosters a mindset of curiosity and resilience. It shows that the biggest questions are still open, waiting for the next generation to bring their fresh perspectives. By engaging with this mystery, students learn that the universe is not a closed book, but an ongoing story, and they are being invited to help write the next chapter. This search for cosmic symmetry is not confined to a single field of science, but represents a grand fusion of human knowledge. Mathematics provides the fundamental language, with concepts like group theory describing the transformations under which a pattern remains unchanged, and topology exploring the possible shapes of the universe itself. These are not just abstract exercises, they are the essential tools for decoding the blueprint of reality. Physicists specializing in condensed matter offer a surprising and powerful analogy. They study how materials undergo phase transitions, like water freezing into ice, where a symmetrical liquid state gives way to a more structured, crystalline solid. This process of symmetry breaking provides a tangible model for how the hot, uniform soup of the Big Bang could have crystallized into the structured cosmic web we see today. The sheer scale of data demands the power of modern computer science, where complex simulations model cosmic evolution and sophisticated algorithms sift through observations to find the subtle statistical signatures of order. This cross-pollination of ideas is essential, showing that the universe's deepest mysteries cannot be solved by one discipline alone. They require a synthesis of perspectives, where a mathematician's formal proof can illuminate a physicist's model, and a computer scientist's code can test them both against the hard evidence of the night sky. This collaborative effort itself mirrors the cosmic web it seeks to understand, where separate threads of inquiry connect and strengthen one another to form a coherent picture of the whole. It is a beautiful reminder that our quest to understand the cosmos often reflects its own principles of interconnection, and that the profound beauty we find there has, for centuries, inspired artists to translate cosmic wonder into forms that speak directly to the human heart. Our ancestors saw the cosmos as a perfect, harmonious sphere, a divine geometry of celestial order. This deep-seated human impulse to project symmetry onto the heavens is etched into our history, from the perfect circles of Greek astronomy to the intricate mandalas of Eastern traditions, each one a spiritual map of a balanced and interconnected universe. Today, that same impulse finds new expression, fueled by the raw data of our telescopes. Modern artists are translating the deep field images and the ghostly filaments of the cosmic web into stunning visual works. They take the statistical hints of large-scale symmetry and render them in swirling paints, immersive light installations, and digital sculptures, making the abstract architecture of the cosmos something we can not just understand but feel. This artistic interpretation is a vital bridge, transforming cold data into a visceral experience of our place in the grand design. This resonance extends far beyond the gallery. In films and literature, the search for a hidden cosmic pattern is a powerful metaphor for our own search for meaning and connection. The lone astronomer peering into the void mirrors the universal human quest to find our role in a vast, often indifferent-seeming existence. When a character in a story seeks a pattern in the stars, they are really asking if the universe has a purpose and if we are part of it. This cultural reflection shows that scientific discoveries do not exist in a vacuum. They ripple through our collective consciousness, providing new symbols and narratives that enrich our understanding of ourselves. The beautiful interplay between science and art underscores a fundamental truth. Our desire to find beauty and order is not separate from our quest for knowledge. It is the very engine that drives it. This investigation into cosmic symmetry is, at its heart, the fulfillment of that ancient human yearning. And as we stand on the verge of such profound revelations, it compels us to look inward and consider the responsibility that comes with this knowledge. How will understanding the universe's fundamental blueprints change our perception of our own place within it? And what will we choose to do with that understanding? This grand pursuit of cosmic understanding is never separate from the world we live in. The immense resources required to build a telescope like James Webb or to operate a global survey demand careful ethical consideration. These are not just scientific instruments. They represent a profound investment in pure knowledge, a choice to fund our collective curiosity about the universe on a global scale. Such a commitment must be made transparently, with clear communication to the public about the goals and the value of this fundamental research. The discoveries themselves, like the potential symmetry woven through the cosmos, belong not to a single nation or institution, but to all of humanity. This is why the principle of open data is so vital, ensuring that a student in a remote classroom has the same access to the raw data as a professor at a world-renowned university. This open access prevents the duplication of effort and accelerates our shared progress, turning every new observation into a building block for a global community of inquiry. The knowledge gained from these cosmic maps may not build a faster smartphone or a more efficient engine, at least not directly. Its value is more profound. It fuels our imagination, inspiring the next generation of engineers and artists and thinkers. It pushes the boundaries of technology, as the challenges of building a space telescope lead to innovations that ripple through medicine and computing. Most importantly, it answers a deep human need to comprehend our own story. From the first quantum flicker of the Big Bang to the grand, structured universe we see today. This perspective is perhaps the greatest gift of cosmology, seeing our world as a tiny, fragile oasis in the vast cosmic dark fosters a sense of shared responsibility. It reminds us that beneath all our differences, we are crew members on a single, pale blue dot, united by a common origin and a shared fate. This cosmic awareness can inspire a deeper commitment to stewardship, both of our planet and of each other. Ultimately, the ethical framework that guides this exploration ensures that our reach for the stars remains a noble endeavor, one that elevates our gaze, enriches our culture, and binds us together in the great, ongoing quest to understand our home in the grand design. Our journey through the cosmos reveals a universe far more structured and mysterious than we ever dared to believe. From the first stunning glimpse of countless galaxies in the Hubble Deep Field to the intricate infant structures now seen by James Webb, we have followed a trail of clues pointing to a hidden order. This potential symmetry challenges the foundational rules we thought governed everything, from the cosmological principle to the very nature of dark matter and dark energy. It connects the faintest quantum whispers of the primordial universe to the grand cosmic web we see today, a story written across nearly 14 billion years. This entire investigation stands as a powerful testament to how science truly works. It is not a dusty collection of facts, but a living, breathing process of collective wonder. New observations constantly test our oldest assumptions, forcing us to refine our models and sometimes to dream entirely new ones. International teams of scientists, armed with sophisticated statistics and powerful telescopes, work together to separate cosmic signal from illusion, proving that the greatest discoveries are made when we collaborate across every border. The universe, it seems, is always more complex and more wondrous than we can imagine. Let this exploration inspire you to look up at the night sky with fresh eyes. When you see that vast, dark expanse, contemplate the possibility of a hidden architecture, a delicate symmetry governing the immense expanse. Every pinprick of light is part of a story still being decoded, a mystery waiting for its next investigator. Thank you for joining this journey to the frontier of cosmic knowledge. We would love to hear your thoughts on these profound patterns in the comments below. And if you are eager for more voyages to the edge of understanding, subscribe for our next adventure into the